This is Jeremy Krans, October 2025, ANA 630 class. This is my NBA player career success and role profiling project, a data mining study of early career predictors and archetype clustering. Let's get into it. Data preparation and feature engineering. How I structured the NBA player data set for regression modeling. So the raw data is NBA season level player statistics, so how they did for the season, their averages, 1996 onward. I included players drafted 1996 or later, so anyone drafted before that is filtered out, and undrafted players are also filtered out. The initial sample size is about 8,500 rows, and I wanted to cut off 1996 just to ensure relevance to modern basketball. I aggregated the first two seasons for each player, so keeping only their rookie and sophomore season with different attributes. Most importantly, the ones we'll be looking at is points, net rating, and games played. The resulting data set is about 1,400 players and their key early career stats. Defining the target variables, peak points, so a player's max points in a season in their career. So where are they going to peak? Career games, so total games played, and career net rating, so their mean net rating over their career. And then merge targets into the early career data set with complete features and target outcomes. Distribution inspection and transformation. So I visualized distributions of the target variables, peak points, career games, and career net rating. And peak points in career games were quite skewed. For linear regression, we want normality of the residuals. So I addressed this via log transformations. So the example here is the peak points. You can see the before and after I addressed with log transformations. Not perfect, but much better. Feature selection and model readiness. So the selected predictors are points, true shooting percentage, usage percentage, assists, net rating, again from the first two seasons. Added constant term for the intercept, and then prepared X predictors and Y targets set for OLS modeling. So the summary of the data prep here for the linear regression was I filtered to modern era, aggregated early career seasons to create a predictor data set, defined the meaningful outcome measures for the long-term success, conducted distribution and normality checks, applied log transformations, and now have a final modeling data set ready for regression and clustering. So model performance. The three models: career games, peak points, and net rating. So you can see here R squared range between about 38 to 83%. The net rating model had the highest R squared, but is probably less useful due to overlapping. I think the best model is actually peak points. And then this is just visualization of predicted versus actual on the log scale. As you can see, career games, peak points, all look pretty good. Not perfect, but all models are wrong, right? And then the real scale, I wanted to see actual games played, not the log scale of it, and actual points prediction. And as you can see, as we get out further to either longer careers, predicting longer careers, and predicting higher points output, the confidence interval widens, just because there's less data for exceptional players than there is for your average NBA player. The model strengths and limitations. Strengths: the early career stats show meaningful signal in predicting long-term outcomes. The peak points model shows solid predictive accuracy. And limitations: the net rating model may be quote-unquote too easy because of early in career net rating overlap. It's typically stays pretty close, early career to late career. Model struggles with extreme outliers, so superstars, due to linear assumptions and just missing features. So health, role changes, just team context. Maybe you're the number one scorer on one team, but you get traded and now you're the number 3 scorer, and just non-linear growth with players that come in and end up becoming superstars. And then here's individual player predictions for a couple players. So I chose Carlos Boozer, Kobe Bryant, Rodney Hood, and Steph Curry. So you can see predicted games is close on a couple. I should note here too that Rodney Hood and Steph Curry are still playing in the NBA. And so those actual career games numbers will go up. So Steph Curry will get closer to that predicted number. And Rodney Hood will get a little bit further away. Kobe Bryant was a tough one to predict on. He actually had a similar early career stats as Rodney Hood, and he came off the bench as a rookie, where Steph Curry was a starter from the beginning. But you can see predicted points for Carlos Boozer, who's an average star player, so not at the level of Kobe Bryant or Steph Curry, but he was an all-star. The predicted points was pretty close, within a few points. Kobe Bryant was off by quite a bit, a 20-point stretch there. But as you can see, it's harder to predict star players, superstar players, that is, especially who had a lot of growth after their first and second year, which makes sense again for Kobe Bryant. He was drafted when he was 17 years old. But for Rodney Hood, really close. 16 was as predicted, only roughly 1.5 point different from the actual. And then Steph Curry again was really close. 36 points per game was his predicted peak, and his peak as of now probably will stay this way because he's later in his career, was 32 points. So the key takeaways and how I would work on this more in the future. So early career scoring, efficiency, and usage matter for predicting career potential, but they don't capture everything. You need richer features, more advanced metrics and context. And so going forward, I would recommend that I explore nonlinear models as well for the next phase. But by leveraging early career metrics such as scoring, efficiency, usage, assists, net rating, etc., the regression models were able to predict long-term outcomes with moderate to strong accuracy, ranging from R-squared of 0.38 to 0.83. These findings do highlight predictive value of early performance, but they also reveal limitations, especially in capturing outliers and structural context. This emphasizing the need to just enhance features and model complexity moving forward. From here, we're going to look at clustering for player archetypes. So overview, the objective is to identify distinct NBA player career type profiles using unsupervised learning. My method was to apply k-means clustering to full career averages. I put the cutoff as players with at least 6 seasons. A typical player will reach their peak within that time. And the goal is to understand what kind of career paths exist, not just games and points. So data selection and feature set. I filtered, again, to players with at least 6 full seasons to ensure able to reach their peak. Aggregated season level stats into the per player career averages, so points, rebounds, usage, true shooting percentage, etc. And then shows features that reflect scoring role, efficiency, usage, playmaking, and rebounding impact. Choosing the number of clusters, I ran k-means for k from 2 to 10, and evaluated both inertia and silhouette score. Inertia curve showed diminishing returns after about 4, and silhouette peaked around 2 to 3. So I ended up selecting a little bit above there, k equals 5, for interpretability in the NBA context. I thought 5 archetypes would align well with different types of roles for different teams and different players. Clustering centroids and archetypes. So standardized features, centroids showed Z scores, so how many SDs above or below the mean. So an example values would be cluster 3 has plus 1.41 in points, 1.18 in usage, and 1.51 in assists. These would be our high volume creators, and I define them as such. So cluster 0, rebounding and inside specialists. So these were typical big men that weren't really scoring a lot. They were there for rebounding and defense. Cluster 1 is your reserve or low impact players. So players that are your reserves, your bench players, but don't impact the game a ton. Cluster 2 is your efficient role player. So this could be players that specialize maybe as 3-point shooters or something like that, but aren't creating their own shot or creating shots for others. Cluster 3 is the star primary scorer, playmaker. So these are typical in this bucket were wings and guards. So think about LeBron James, Steph Curry, Kobe Bryant, the star guard players in the league. And then cluster 4 is your star big men, dominant forwards and centers. So players that have high efficiency, great at rebounding, and also good scorers. So here are some example player assignments. So mapped specific players to clusters. So if we take a look at Steph Curry, he ends up in that cluster 3. Rudy Gobert in that cluster 4, and then Rodney Hood in cluster 1. And showed how clusters distinguished guard and wing stars versus dominant big men versus role players and specialists. And also offers concrete validation that the algorithm's grouping map to real-world NBA roles and trajectories. So as you can see below, cluster 1 is your just kind of average or below average player, not high impact. Cluster 3, high in assists, well over the average, high in usage, shooting percentage, still above average, points way above average, but not huge on rebounds, because these are typically your guards and small forwards. And then cluster 4, these are your stars that are tall. So your Shaquille O'Neals of the league, Rudy Gobert's, while not a high scorer, super efficient, lots of rebounds. Your Karl Anthony Towns type players. Prediction plus archetypes and next steps. So the regression models estimate how much outcome. So games played, peak scoring, while clustering defines what kind of player they are. So high use shooter or dominant big man. Strategic context. So knowing the cluster membership of a player adds an extra dimension of forecasting and can help refine prediction accuracy. Going forward, that's something I would actually add to the linear regression. Limitations here: aggregating career averages. does overlook time series changes. Players often change roles, which can blur the cluster boundaries. So next steps would be to incorporate archetype label as a feature in the regression model, as I said before. Expand the feature set with advanced metrics and contextual variables. So again, injuries and role on the team. And explore nonlinear models. So random forest, gradient boosting to capture those more extreme career cases where there's nonlinear growth from rookie to star of the league. And then I just added some slides to the appendix here. Here's the cluster map of the players. So you can see the clusters there. And then I also added all the players in each cluster if you're interested. Cluster 0 had 221, cluster 1 had 257 players. As you get better players, you have less, obviously, in each cluster. So these are efficient role players, there's 178. Playmaking, wings and guards, 144. And the smallest cluster are your star big men with only 102. And that's it.